Hello, welcome. Good to see you. Hasn't been a little while. So we're going to be looking today at trig derivatives. As you can see in our title, trig prime. So we're going to start off by sort of verifying or showing where does the derivative of some of these trig functions come from. So I'm going to start by doing the derivative of sine of x. So we're going to look at our friend, the definition of a derivative as we work this out. So I'm going to take the limit as h approaches 0 of our function. It's going to be f of x plus h. So that's going to be sine of x plus h minus sine of x all over h. We're going to look at this definition of derivative, that instantaneous slope, that slope at one point. And we're going to figure out what we can do with this. So if we look at this sine of x plus h, when we did trigonometric stuff last year, we had those various formulas and identities about trigonometric functions. One of them was on sine of u plus v. And if we expanded that out using that property of sine of u plus v, okay, I'd have the limit as h approaches 0. And I'd expand out, it'd be sine of u cosine v, so in this case sine of x cosine h, and then plus be cosine x and sine h. So that's one of those trig properties we learned last year. And then minus sine x still, it just drops down. That's still all over h. So where we're going to go next here, let's see. So I'm going to take the sine of x here, sine of x here. These two terms both have sine of x, and I'm going to factor that out. So a lot of this proof here, just in case you're curious, this would be something if somebody were coming up with it on their own, it would be a much more convoluted process. It would take quite a while. We're doing sort of the version where we basically know what it is we're doing, what the steps would be already through some trial and error that you're just not seeing. So I took that sine of x for the first term and the last term up above, and I factored it out. So I had cosine h, and then from this one, it's just minus 1 now, and then plus cosine x sine h. So what I can do then, when I got my limits, one of our properties of limits we're going to learn about is if I've got this stuff plus this other stuff, is I can break it apart into two different parts. I can separate it out, the limit of the one part plus the limit of the other. So I'm going to take this first part, sine of x, cosine of h minus 1. That's over h. And I'm going to do the separate limit now. As h approaches 0, I'd have the cosine x sine h all over h. So I'm just separating it out into two separate limits. Next step I'm going to take is I'm going to look at like the sine of x here has nothing to do with h. This limit is dealing with h approaching 0. So this sine x that's being multiplied by stuff, I can essentially just take that and put it out in front. Same thing with this cosine x over here. I can bring that out front. So I'd rewrite this whole thing here, put the sine of x out front, and then I'll have this limit as h approaches 0 of cosine h minus 1 over h. And then similarly, I'm going to pull that cosine x out because it has nothing to do with h. I'll have that limit as h approaches 0 of sine of h over h. And now if I'm looking at these two limits here, I'm going to basically take those and we evaluate our limits just like we were doing a couple chapters ago. One of our main ways of evaluating limits would be to type it into our handy-dandy grapher. Take a look at that. Trey says h approaches 0. You wouldn't get any value there, but if we look at values very close to 0, we'd be able to find what that's equal to. So what you should do is probably pause me here and graph cosine x minus 1 divided by x and look at what that limit is, figure it out. Same thing with sine x over x. If you do that, graph that and figure out what that limit is as it approaches 0. So if you pause and do that, that'd be beneficial for you. If you did, hopefully you did to play along here. When you graph that and you approach 0 on both sides, this is going to be equal to 0. So that's just times 0. the sine of h over h. That might look familiar. I think that was the very first limit we really looked at and graphed and such. And if you graph that one, you look at both sides, that would be approaching 1. So when we work that out, the sine of x, or times 0 is just 0. Cosine x times 1 is just cosine x. So when we did our derivative of sine x, originally that's what we started with. Eventually we got all the way down, we ended up with cosine x. So we can just in general say anytime we're doing the derivative of sine of x, so d dx sine x, that's going to equal cosine x. And that'll be one of our very useful formulas here as we're doing trig functions. If we're looking at cosine x, if I wanted to do the derivative of cosine x, I could go through with the definition of a derivative doing similar to what we just did over those last few minutes. But I'll just give this one to you. You'd end up through a similar process getting that the derivative of cosine x is negative sine x. So we got those two. And now if we know those two, and those two both come from doing the definition of a derivative and working that out, going through those steps, we only did the one of them, but you could do the second one as a practice if you were motivated and inspired on your own. We can use those two then to find any of the other trig functions. I'm going to work out, let's say if we wanted to do the derivative of tangent x. What we can do then is I can rewrite tangent x, because tangent x can be written in terms of sine and cosine. Hopefully you remember from trig stuff, one of those really important identities. Tangent x is the same as sine x over cosine x. So if I'm looking at that, sine x over cosine x, that's a chain rule. Or not chain rule, you haven't talked about chain rules yet. That's a quotient rule, or quotient, we got a division. So I can use the quotient rule. So my u would be sine of x. My v would be cosine x. And we now know the derivative of sine x, written right up above there. The derivative of sine x is cosine x. And the derivative of cosine x is negative sine x. And if I plug those into our quotient rule that we learned a little ways back, you hopefully still remember. We have v du, so v and du, that's cosine x times cosine x. And then minus u dv, so u is sine x times negative sine x. And that's all over v squared. So all over cosine x squared, or cosine squared x is how you would usually write that. So if I have cosine x times cosine x here, cosine x times cosine x would usually just be written as cosine squared x. Negative sine x times negative sine x, that's going to end up being then plus sine squared x, all over cosine squared x. And if you're looking at this top part here, cosine squared x plus sine squared x, usually we'd see it written the other way around, sine squared x plus cosine squared x. That's another one of our very useful fundamental trigonometric identities. If you looked on your unit circle sheet and stuff, you'd see that is equal to 1. So we'd have 1 over cosine squared x. And 1 over cosine is also could be written as secant. So 1 over cosine squared x could be equal to secant squared x. So we'd have our derivative of tangent. That's what we started with. So the derivative d dx of tangent x is going to equal secant squared x. We could do a similar process. We could look at the derivative of cotangent. You could rewrite cotangent as cosine x over sine x and do a quotient rule, much like we just did there. And if you work that out, you would get negative cosecant squared x. So that would be another one of our trig functions. The last two, secant and cosecant, we could do the similar process. Like if we were doing the derivative of cosecant x, let's say, and we wanted to work that out. The derivative of cosecant x would end up being negative cosecant x cotangent x. And the last one, our derivative of secant x, would end up being secant x tangent x. So we'd end up getting those 4 there, plus our other 4 that we had, or the other 2 we had up there. So those are our fundamental ones. And we'll go on here in a follow-up video and go through an example using these, just work out a general derivative.